Thanks, Ashwin. Welcome back. Yesterday we were talking about clouds and convection. We also talked a bit about radiation. Today we'll talk about simple models of monsoon variability. And let me start by showing you this, which is the latest from India Met Department. I don't know how many of you have the habit of checking such a plot, such a graph. You can raise your hands if you have. Okay, so I will say 30, 40%, 40, 45%. Okay. So what this shows is, in the red is normal dates of onset. That means on all these kind of locations, usually monsoon onset occurs on a particular day. And we saw that this year until 22nd of June, we did not have anything and then started cranking up. You can see that from here. Look at 11 to 23rd June. The blue line goes all the way and then boom, right? And it's all over the ocean. Nothing is over the land. And just on 24th June, you see a significant migration. And in just a couple of days, it's already crossed. So somewhere in central Maharashtra or Karnataka, you can say that monsoon was already here on time, or maybe 3-4 days delayed. But in Delhi and Rajasthan, you can say it's already arrived, which is a week ahead. It's a bit of an anomalous thing that has happened this year. Since we will talk about monsoon variability, I thought I should also show you what is the status of rainfall until today. And you can see that most of India is in deficit. Regions in northwest are in surplus. You can already see that because monsoon did a quick progression. The rainfall there is already surplus. There are regions where, so you can see that the deficit is in some regions like say Maharashtra or Jharkhand, West Bengal, the deficit is of the order of minus 99% to 60%. So we'll all have to be worried. I mean, especially those who are here or there. I think in Karnataka, it's not bad, but so in some sense, the variability of monsoon, how rainfall will form patches over different parts of India, over different time scales and length scales, will really decide if this all becomes normal, which is green, or some patches remain above or below normal. Okay, let's look at an animation again to see what sort of variability are we talking about. So as you can see, there is this 6th of June, and this is a, you can say, 2014 season of monsoons. These are clouds. You can see there is a kind of cyclone in Arabian Sea that started. By 13-14 June, you already had some convection in the Bay of Bengal, some of it already encroaching towards land. You can also notice that in terms of rain, now clouds have shifted to rain and rain. So there is a large scale variability of which Indian monsoon is a part. You can notice, for example, there are some systems which start from Bay of Bengal and start and migrate north-westward to give significant rainfall across India on fast time scales. But there is also a slow time scale variability, which I'm sure you will not be able to observe here, is that of something like 30-day variability in rainfall, where rain bands start somewhere near equator and move northwards. Or if you think of a bigger rain band, this part of rain band starts moving towards India, whereas that part of the rain band kind of sticks near to the equator. And this happens over kind of 30-day. So I won't call it a wave just because maybe oscillation is the better way of calling it, because one way migration from south to north occurs, but the other way does not. So it flips back here and again starts from near equator. And we will want to talk about all these variability. To understand monsoons, you should also distinguish between summer versus winter. I'll not bore you with what all you already know. Just try to appreciate that monsoon is sitting in the background of wind flows. So rainfall patterns and wind patterns, seemingly, I mean, winds will ultimately bring water vapor, energy, and so on. But rainfall many a times do not have a direct correlation with it. So there's a lot of dynamics that you need to model to get how winds talk to rainfall. Okay, so there's a lot that you could explain based on temperature, what drives. I'm sure you have heard about land-sea contrast theory, which we'll talk about a bit. But let's move on to our favorite diagram where x-axis is time, y-axis y-axis is time, x-axis is spatial scale. We saw what all modeling tools and phenomena occur. We will want to talk about synoptic scale, where I was talking about low pressure systems. These systems start from head Bay of Bengal and migrate northwestward towards the desert in the course of a week at the max. And while they do so, they distribute rainfall. And these are spinning vortices. Then there is northward propagation of convection on intraseasonal time scale, 30 to 60 day mode. So that means during a season, you can have 2 to 3 such northward migrating rain bands, which bring rainfall from Indian Ocean to the Indian landmass. And then we will also want to look at ultimately seasonal features, why at all there is monsoons. And we will want to talk about some simple models that people have constructed. Throughout this talk, I might rush through some of the models, but the idea is to expose you to the type of models that were constructed to look at this variability. Sometimes I may have to rush because there are too many details. If you are missing the point about how the model was constructed and why was it constructed, then stop me and ask. But if
I'm happy to be here.
Me too. But if you think that there are some details which are missing, we could discuss them at the end. Yeah. So why is this model constructed? How it is constructed? On top of what all we discussed yesterday. Okay. Yeah, I will maybe skip this slides, but ask you this question. How many of you think that cloud clusters actually migrate with winds? Raise your hands. Few of you. So clouds migrate. Yeah. So the answer is clouds do not migrate with winds on these large scales. Clouds have a lifetime of around few hours, right? And you can do the calculation and see how far can clouds go if they were to just be advected. You can say that conditions that make cloud migrate and the clouds kind of sustain generations after generations on top of the background that the energy that sustains clouds it sustains. So again, this is a seasonal cycle where June, July, August, September, July, August being the most important months. There's a funny quote from Pranab Mukherjee who said, monsoons are the real finance ministers of India. So all the more reason to study monsoon variability. The speaker after me probably will talk about this in the greater detail. So I'll quickly say that there is intraseasonal. So apart from synoptic to intraseasonal and seasonal variability, there is intraseasonal, interannual, decadal, and millennium and longer variability, influencing different features and also in being influenced by several other phenomena occurring across the globe. I think Suvarna will speak about this a bit more. So let's get going with simple models for seasonal cycle. Let's look at again that animation, but this time a bit faster. And I want you to appreciate how starting from June to October, how monsoons enters and retreats. You can notice that although the migrations are from south to north, the rainfall actually has a tilted axis. So you can see that it comes from somewhere southeast and goes towards northwest. And that's the axis of monsoon, if you like to think of an axis along which it likes to move. And the idea is, why does it do so? So you must have noticed winds cross equator and come towards India in response to heating, but the rainfall comes almost perpendicular to it. So there is already some hint here. I think Jim mentioned yesterday that background state is many a times geostrophic, but geostrophy will not give you much of a divergence. We don't have time to show you. It's simple. You can take a dot product with del and show that, take divergence basically and show that it's small so far as there is. But rainfall actually does so. So there is a non-divergent component of the flow which gives you rainfall. which sits on top of geostrophy, which matters. And the whole idea is to kind of model that. But let's not complicate picture. We want to model seasonal cycle. I'll talk about three very simple models that people have been talking about. And what do they want to do? They want to kind of write a model why this rain band, which is an average rain band between 65 to 95 degrees east, and as the season progresses, why does it flip from southern hemisphere to northern hemisphere and back? That's the kind of aim of the seasonal cycle model. So let's look at the first model, which appeals to simple land sea column contrast. And here the idea was for basic understanding. I think Jim talked about hydrostatic balance, and by and large, tropical atmosphere is in hydrostatic balance. So they said, why not start from hydrostatic balance? So your dopey-dozy is proportional to G by, so I have replaced rho with P by RT bar, where T bar is in some sense average temperature of the column that you want to consider either over land or over the ocean. And you could apply the same equation for these two columns with T warm and T cold being the appropriate ones. And we want to see if land column is warm versus the ocean column, how will the circulation want to respond to this? So you could integrate this and get an expression for, say, log of P as a function of some, so G and R are constants, so far as you have the gas is given to you. Z1 is the altitude at which P1 is looked at. Tc is the column temperature of the cold column, that of the warm column, and this is at the surface. And you can appreciate this better in this particular plot. Maybe we will, for the sake of simplicity, this is if you were to treat the whole thing as dry, then that's the leftmost column. If you were to treat it as moist, that's the rightmost column. And there are several limitations of this which we will discuss later, but what you can see is that temperature decreases as, say, a particular profile which is a dry-like profile, whereas this, whenever there is convection, it will decrease a bit more moderate, and associated with that there will be mass displacement, and associated with mass displacement there will be pressure gradients. So near surface you will have pressure gradient towards from the warm column, from the cold column to the warm column, and above exactly the opposite. And that's the critical condition that needs to be followed under this framework, that the temperature of the warm column should be greater than a particular threshold. And then so far as this happens, then you can say monsoons have onset, or you can otherwise say that flow from ocean to land in the lower troposphere, and exactly probably opposite the upper troposphere has already happened. So this simple way of thinking is good conceptually, that you are saying, oh, there are two simple columns, but how can we use this? Because we ultimately want to predict winds and precipitation, and this does not lead you anywhere, because precipitation is not the diagnostic term here, neither is wind. And actually, if you see that the warm column becomes warm because precipitation occurs there. So in some sense, you are giving a criteria which is an after effect of precipitation. So although conceptually good, this is, I mean, you can't push much in terms of this thinking. So let's move on to see another empirical model to represent changes in monsoon rainfall. And this particular model by Leverman appeals to a feedback where he says land-ocean temperature difference will drive monsoon winds. Monsoon winds will advect water vapor, and because they advect water vapor from land to ocean to land, you will have latent heat release because convection occurs, and then there will be a feedback on land-sea contrast. So let's look at some of there are 4 equations in this. This is a heat balance over India, where he's trying to say that heat generated during monsoon cloud formation, which is LP, P is precipitation, is balanced by heat emitted away through radiation or heat given away to adjacent regions, advection. So advection, radiation, and generation through condensation. That's simple kind of one equation. Wind generation in this particular model is proportional to the land sea contrast. So you can just say that this is a proportionality. Larger the temperature difference, more the winds from ocean to land. You can say that because these winds carry water vapor towards land, you can write a simple balance saying that if it precipitates over land, it has to be because winds acted on moisture gradient between ocean and land. So you can write a simple moisture balance and then say that, oh, you ultimately want to create precipitation out of water vapor. So you can say precipitation is proportional to the amount of water vapor that the winds were able to advect. And then you can have a nice simple system. Notice here that this model is stretched to a limit of simplicity so that you can get a closed form solution. You are getting away with the differential equations, something that we talked about yesterday, others also talked about. Here the idea is, so far as this holds true, you want to look at how stable is this system, because in some limit, this may or may not, I mean, this looks physical. So then you can solve this system and make a cubic equation out of this. So there are few parameters. You can kind of put some of them together and have this system where there are only two parameters, L and R. L depends on ratio of moisture and heat advection, and R is a measure of radiative energy input. So what you then do is pick L and look at which values of R give you real solutions. By the way, so that's what you do. Maybe let me ask you, so cubic polynomial usually has how many real solutions? How many think? At least one, yeah. So one, you are ensured in this that there is one solution which will work out. And these diagrams here on the left, I'll not go in great details, but they show that there is a critical value of either radiation R or that of W, beyond which monsoon solution is not available. Monsoon solution being winds from ocean to land. And this black curve shows that critical limit for different values of L, which is the ratio of advection of heat and moisture. And then Leverman and colleagues said that, see, this is the solution we get, and that means below a critical value of R, that is the radiation input that you input over the Indian land, below this, you may not have monsoons at all. And if that were to be true, and if we are doing something crazy with the system in terms of changing that radiational energy input, then we could have catastrophe. So this paper made some noise, but later on, this paper was criticized as well. So careful scrutiny showed that this model assumes that heat is produced and advected out or radiated away. But what happens in tropical atmosphere, tropical troposphere especially, is that the largest gradient is not in the horizontal, in temperature or energy variable. It's not in the horizontal, but it's in the vertical. And that means the way you have constructed model itself needs to have vertical advection as opposed to the horizontal advection. And if you were to add that, then you show that nonlinearity disappears or becomes weak. And I guess Ashwin will talk a bit about this. Rather, he's worked on this model and maybe improved it, so you can hear more from him. The other thing is climate model experiments have already shown that these large, when you basically hit climate model with a large energy input, you don't see nonlinear changes that Leverman and colleagues predicted. So this model is great again because it pushes you to a limit and makes you think of monsoons in the most simplest form. This is a great exercise that they have done. It has limitations. All studies have limitations. This model also has limitations. Okay. Now, so until now we have talked about one model which is pure hydrostatics, one model which couples moisture, momentum, and energy equations in a very simplified form. Now let's look at something which throws away the momentum equations all the way. It just says, I'm just worried about energy. How much is energy, either in terms of internal energy or water vapor? And I'll just keep track of energy. And the hypothesis is that there's a particular conditions which monsoon circulations need to satisfy so as to exist. And that condition is these circulations should export energy. So if you keep track of energy and look for where there is an export of energy, surplus of energy, so that it's given out away rather than importing it from adjacent regions, then you can say, oh yeah, I already have a model and I don't want winds and so on. These slides are thanks to Chetan Jalihal, who worked on this particular problem. So based on moisture and moist-static energy, something that we discussed, moist-static energy you could write down as in a steady state. If you want to have a steady model for monsoons, as whatever energy you input in the column of over the India from either from top or bottom is either advected vertical or in the horizontal direction. Same for moisture. In the process you produce precipitation, E is evaporation. And then you could construct a model out of this to calculate P minus E. And that model looks like this, that you can put everything else on the right hand side and P minus E on the left hand side. So energy input or a parameter which clubs all the dynamics, all interesting dynamics is clubbed in one parameter. If you were to do this, this is what and then you say monsoons are systems that export energy. If you were to say this, then there's this one more simplification this model does. So what this model shows is this particular parameter which clubs all the advection vertical or horizontal of moisture or moist-static energy can be simply written as a function of column water vapor. So what this shows is column water vapor on x-axis, y-axis is that parameter which clubs everything. And you can show this is a nice hyperbola. So you can just say this is some constant by column water vapor, basically fit some hyperbola, which is a lower bottom equation. And then you have a simple equation, right? Precipitation over land is evaporation produced locally or some amount of energy that is utilized in efficient way given by this equation. And you can show that the right hand side plot is from Srinivasan 2001. You can show that for different monsoons, India, South America, North America or South Africa, you can basically reproduce observations in solid dots with simple model. Simple this, you for each of these regions, keep on calculating net energy input, calculate local evaporation, have water vapor. So these three parameters. And then you can already predict the seasonal cycle that will go up and down. So what is kind of surprising is that you can do the same and explain variability of monsoons for past 21,000 years. So this plot shows, say, monsoon variability in past 21,000 years as reproduced in a climate model, which solves full set of difference equations. I mean, you convert PDs to difference equations and solve it numerically. And this is from the diagnostic model. And you can see, I mean, it by and large captures what happened there. So for seasonal and longer variability, you could have some model already based on just moist-static energy and water vapor. But what this model, can we use this model for a season? Not, because you can't get winds out of this. So there are models which can give you wind, models which can give you precipitation, but one would ideally want a model which gives you both. And neither of these models do that. And that's why we should kind of, that's an open problem, how to club dynamics and energetics together to produce a model which works at all these different time scales. So I have tried to tell you about three different models. Now let's look maybe a couple of minutes on natural versus forced modes of tropical atmosphere. There has been a lot of discussion yesterday on internal waves, also some shallow water equations at the beginning, a bit of turbulence. Let's look at how people have thought about this for the atmosphere. So if you were to hit atmosphere, assume that atmosphere does not have any basic background flow. And if you hit it with some small perturbation, then what sort of modes that you will have on sphere is the question we are asking. And usually people start from this set of equations that we have been talking about, where m is the mean flow, which will change seasonally. F is the scale interaction. Sometimes the scale at which you are interested in is forced by or interacts with some other scale. Sometimes there is a particular background profile on which some of these modes sit. So this is a kind of generic framework that you can think of. So something called Matsuno-Gill model, which tries to give you neutral modes. So that means you are not forcing it with any finite amplitude forcing. Remember, we said if you want to look at convection, you need to hit it with finite amplitude forcing. If you do it with infinitesimal forcing that others were talking about, you usually kind of and you kind of forget about mean flows, add Rayleigh friction, Newtonian cooling, which are kind of dissipative terms. Then you can get some dry modes out of this system. And Matsuno showed this for the first time. If you prescribe one of this, you add some energy in the system, then you call it forced mode, and Gill gave you these solutions. I'll quickly go through, maybe I don't have much time, but I'll quickly show for the sake of completion what we get out of this. So here, all the lines are solutions of that system that we looked at. Those who are interested in wave dynamics, there's already one very interesting feature of this set of equations is that the solutions they look like, actually they are given by Schrodinger's equation and in the form of Hermite polynomials and so on. So you could look at equatorial wave theory for this, and the solutions look like this. The lines here show the kind of analytical solutions from Matsuno's analytical problem, and color shows here actual observations, and you can see how well Matsuno's theory reproduces different waves. Either Kelvin wave in the symmetric spectrum, something symmetric about equator happens the same at the same longitude, north and south of the equator, or in the asymmetric component. So you can see Kelvin waves, Rossby waves, or mixed Rossby gravity or inertia gravity waves being reproduced. What it does not reproduce is Madden-Julian oscillation. Neither does it produce what we have in the monsoons. So Madden-Julian oscillation and intraseasonal oscillation, which is asymmetric component, which is filtered out here, is not being reproduced. So you need to do something more different from what Matsuno did to explain these. And people have been trying for a few decades. Let's look at what will happen if these are not neutral modes but forced modes. So that means you add a heat source of finite amplitude and look at the steady state solutions. Gill in 1980 did this. This is again a very nice paper. Those of you who are mathematically inclined can look at this particular paper. Very beautiful analytical solutions to get a mixed Rossby and Kelvin wave response. Kelvin wave will migrate eastward in a steady state. So far as you have a heat source going on, Kelvin wave will keep on generating, and Rossby waves away from the equator will keep on generating. And there's a steady state response which looks like a bit like Walker circulation. So this was Gill's kind of solution. Then Gill did another thing. Instead of having a symmetric heat source, he migrated this heat source away from the equator, and also showed that if you do this in the steady state, you develop some cross equatorial flow, which kind of forms, which likes to attach to a Rossby wave like gyre away from the equator. And some features of this are also like that of monsoons. And so you can already explain some aspects of cross-equatorial flow and the gyre-like vorticity generation using Gill's simple model. The problem in this model is that heating is given and response is observed. But what happens in atmosphere is the flow itself will decide where heating is decided. So there's a close feedback. So this model will say, oh, no, the heating likes to sit here. Let me look at the response. So that's the problem in this. Okay, so now I have told you a bit about how people usually think in terms of kind of single layer or shallow water solutions. Let me look at let's look at kind of intraseasonal variability and what models people have proposed for this. So I told you there is a northward propagation. This is seen at different longitudes. X-axis is time, y-axis is latitude. So with time, these different rain bands, so I think this is outgoing long wave radiation plotted here, which is a proxy for high level clouds. These high level clouds start from somewhere near the equator, and with time, they migrate northward. And the usual phase speed is something like 1 degree per day. So that means around 100 kilometers per day. And if you want to construct a model, you want to construct a model which gives you an unstable mode. The neutral modes do not give you already this variability, right? So it has to be some unstable mode which is able to trigger convection. It should give you a phase speed of around 1 degree per day. And it should also give you some growth rates which are sensible. That's the kind of challenge for any model that you would want to propose. So the model, so what people did then, have I skipped a slide? No. I think this should have been before. So what is the background state in which the intraseasonal variability sits? You can see that there's a vertical shear, U200 hectopascal minus U850 hectopascal gives you some contours of -25, -20. That means there's a jet in the lower level, there's a jet in the upper layer, and there's a strong shear. There's also some shear in the meridional winds, much more over Bay of Bengal than Arabian Sea. And also there is a background kind of boundary layer humidity gradient which increases towards India. And this should serve as the background state for all these models. If you do this, so you take away this background state, track the convection. Abhik and his colleagues did this kind of difficult exercise, and they looked at for a convection sitting at 0 degree kind of latitude. X-axis shows latitudes and y-axis shows height. How does the vertical structure of different variables in observations look like? And they showed that if convection is at 0, there is a vorticity signature which is kind of positive vorticity, which looks like a barotropic or uniform vorticity signature to the north. And this was already exciting. They said, oh, so that means we need a model which will explain why is there a barotropic vorticity to the north of convection. So far as we do this, then the second thing would be to explain how barotropic vorticity would generate convection. And so far as we do this, there is a feedback loop, and you could go on. So to do this, they reconstructed a model. You can notice that now we are talking of vertical shear. That means you need at least 2 points to define it. You cannot do with single layer. Something Jim mentioned, I think you mentioned about multiple layers of shallow water. It's a bit like that, multiple layers of shallow water. And then what you do is you write momentum equations at both these altitudes. You add a boundary layer. I will not mention much. You can write down there is a problem in these models called CISC catastrophe. That means if you were to take the shallow water equation, shallow water system, add some amount of heating, force it basically, and look at unstable modes, it so happens that the smallest wavelengths will want to grow fastest. And that does not help you because you cannot then explain why convection really occurs at a particular length scale and so on. But because that happens, what you then say is something else is damping and giving you a scale selection. Scale selection is the other key term in the stability analysis, which I will not talk about. But you then say that some friction process is giving you a particular scale. And then you can kind of form a closed form set of equations, define some barotropic and baroclinic mode, where pluses are barotropic, baroclinic. You take either cross product or dot product with del and construct a vorticity divergence system. Vorticity, either barotropic or baroclinic, is dependent on some of the terms which depend on shear. So UT, VT all are shear in the background flow. So they either generate or destroy vorticity. And we keep track of this. There are usually advection, tilt-in, stretching term. If you have looked at vorticity, you'll notice that you can map that to here. And then you I am kind of skipping a lot of steps to tell you that you can explain so far as there is a, if you don't know what I am talking about right now for next couple of minutes, forget about it. I'm just going to say that there's a baroclinic divergence, which, yeah, forget about it. What it shows is you can explain with, if so far as there is vertical shear given and gradient in baroclinic divergence, you can explain how positive vorticity is generated to the north of the convection. And this positive vorticity through the feedback on boundary layer can generate convection again. So this model then says, oh, okay, you can explain things using vertical shear in zonal winds and meridional winds. There is a particular growth rate and phase speed that this model predicts, which is a function of these shears, which are kind of 1 meter per second or whatever we observe. The major limitation in this model is the boundary layer, which really gives you scale selection. There, we don't know what is the right friction parameter that you should tune. And that means that's the fudge factor. I'm one of the authors in this, but it's the fudge factor ultimately. The other way you can think of this is that you can say that there is a background boundary layer moisture gradient, and then that background moisture gradient can have, if you know what, decompose it in the mean and perturbation state. You can say that background moisture gradient acts on the anomalous winds to modify state of atmosphere to the north, and so far as that happens, your convection will want to move. One limitation in this sort of analysis is this: usually whenever you add moisture in the mix, very few studies have done a proper stability analysis. So you don't look at modes. You by and large give a mechanism and forget about it. So there's a lot of scope to add moisture in the mix, couple it to the dynamics, do a proper stability analysis on top, and then look at which modes survive and so on. One has to be careful because you can't still do what we did, linear perturbation analysis. You'll have to add finite amplitude perturbations. Okay, so this was also observed where tilting was seen. So x-axis is, in this case, I think days, y-axis is latitude. People looked at observations and found that this mechanism might work, that of vorticity tilting and producing positive barotropic vorticity to the north of convection. I'll skip this slide, but just kind of give you a synthesis of what hypotheses have been proposed. So there, if you look at barotropic vorticity budget, several of other studies have either said, oh, no, in this particular model, either mean baroclinic tilting is important, baroclinic advection is important, stretching is important. The point is, in me showing this, is the jury is still out. We still don't know what really controls migration of convection to the north. And so we still don't know. Similarly, there are several papers showing different terms in moisture budget that they find is causing moistening to the north of the convection and migration of these convective systems. Mind you again that here all these systems are kind of forced response of whatever model we have. We started with single layer model. We have now looked at 2-layered models. There was also an attempt in 1993 to see these northward migration of convection as mixed Rossby gravity wave, which is modulated by the delay between convergence, which will cause clouds and precipitation. And this delay in this model is the fudge factor, which gives you the scale selection. I'll not go in great details of how this model was constructed, but my point being, usually you want to look for what gives you the scale, what gives you the phase speed, what gives you the growth rate. And people have tried to look at this in some detail. Okay, now let's go on to see. So now we have looked at simple models for seasonal state, which were very simple models. Then intraseasonal, where convection was moving northwards, and the idea was to explain why that happens. And now we are moving to synoptic scales. That means the vortices form over Bay of Bengal and migrate northwestward. And the idea is, why do they migrate? If they migrate, how do they produce precipitation? So I'll not be able to go in great details of how people for past 30, 40 years have been thinking of this. I'll just summarize by saying that people have been thinking of baroclinic instability mechanisms, which are usually are applicable for mid-latitude atmosphere. Because people saw there is a shear, so through thermal wind, there could be some mechanism of accessing that energy in shear and produce some motion. But they have not been successful in explaining these vortices moving northwestward. The current way of looking at it is, so we in some sense have convinced ourselves that neither baroclinic instability, traditional way of looking at baroclinic instability, or barotropic instability mechanisms in the conventional sense are successful. But what people are trying to do now is to actually produce kind of prescribe shears, either zonal or vertical, and then think that there is a nonlinear amplification mechanism which is akin to one of these baroclinic barotropic instability mechanisms, which talks to the moisture gradients. But this is once you add in nonlinearity, you need to do numerical solutions. So that's what this particular work did. So just to highlight how low pressure systems migrate, look at on 19 July how systems will form here in 3-4 days. You will see that they move northwestward. So look for it. Yeah. So this is in precipitation. So this is a kind of vortex starting hanging around here and then migrating northwestward, and that will leave some impression on the rainfall, accumulated rainfall that you get. If you were to look at this in vorticity plane, you will see nice vortex spinning, but in terms of precipitation, it is all over the place, and precipitation occurs only in the corner of the vortex. And the idea is, how does vortex talk to the precipitation that is embedded inside and keep on deriving energy both ways? How does precipitation take energy from vortex to form and rain out, and how precipitation feeds energy to the vortex for it to sustain? So and usually if you look at these low pressure systems, they start from head Bay of Bengal and migrate northwestward. This is between active cycle and break periods when rainfall is not occurring. You can see that you can map them to either low pressure systems being there or not there, that vortex system. And then this particular model then says we want vorticity divergence coupled to mass conservation and humidity. And humidity has a sink of precipitation. So source can be advection, or so there is some background amount of humidity that is put in. So this is the parameterization used, and you want to kind of integrate this system with some background flow and perturbation on top. What this shows is, as a function of latitude, humidity increases as you go away from say 10 north to around 27 north, and zonal wind actually also kind of has a shear. So they say that probably this is important. So what we'll do is we'll prescribe this in this form. And since they are solving vorticity divergence, they prescribe a saturation profile for background humidity and add a vorticity strip on top of this background flow. And then let it go kind of in time and see what solutions you get. So they did several realizations. When there is no shear, but only moisture gradients, here the color is rainfall, contours are vorticity, positive or negative. And you can see that, oh, this particular feature with no shear, but only moisture gradients, you can already see that precipitation is favored in the corner. That feature you can see already here. When moisture gradients are zero, that's not so. You just get whatever is the background. So this shifted to the other corner, that's already some positive, consistent with observations. When there was only shear, no moisture gradient, things get stretched out in the horizontal and you produce more complex patterns of vorticity. But neither of this or that gives you really the sense of how rainfall and vorticity are interacting. So they did some additional simulations where, unlike in these two, where the perturbation was small, infinitesimal, they added finite amplitude perturbation on top for the vorticity. And then they started seeing some coherent vortex, which gives rainfall on the whatever southwest corner of the vortex, something that is observed. They did other kind of interesting things with either with weak vortex initialization or finite vortex initialization with different basic states to kind of bring more realism in the mix. But the point is, so far as you give enough kick in terms of vorticity and you have some ability for interaction between rainfall and vorticity, you can generate some reproduce some features of what is actually observed. And these are actually nonlinear simulations. So this is where we are. We have realized that we probably need an intermediate approach where we cannot understand full complexity GCMs or weather forecast models or cloud resolving models. Linear stability analysis or analytical models are too simple, they do not capture enough of the dynamics. So why not we go in the intermediate and put in these equations and find the numerical solution, something that engineers have been doing for some time to understand small scale flows. Okay, so take home message from this is monsoon has significant variability on 3 different time scales and several others. We talked about these 3. We do not yet have a simple model that explains seasonal features, which explains both winds and precipitation, seasonal features of wind and precipitation. Models for intraseasonal variability suggest disturbances grow, deriving energy from the background state, vertical shears in zonal and meridional winds. There are also models which kind of suggest that background moisture gradients could be important. There is an open question of coupling these two dynamics, moisture and dynamics together. For synoptic scale variability or those vortices, low pressure systems, we have just begun to use shallow water models to understand vorticity convection coupling over the course of few days that low pressure systems live. Yeah, with that, I'll stop and maybe take questions.
Are there any questions?
Hi, thanks for the talk. I had 2 questions. The first is the Monsoon equation that you showed. Could you briefly tell me how it's different from the inelastic approximation of the atmosphere?
So here we are not doing, sorry, which equation?
Both the one you showed and the before this, yeah, this one. This is linear to start with, and other than that, are there any?
So all the mean flows are here. So this is just a perturbation flow on top of, yeah.
Oh, okay, thanks. And the second question is relating to hydrostatic balance. You talked about how the most simplistic layer use hydrostatic balance, and when you went to shallow water, that also has a hydrostatic balance approximation. But in atmosphere during the day, there is hot air below, cold air on top, whereas during the night it's cold air below and hot air on top. And even when it rains, the land becomes cooler. So my question is hydrostatic balance a good approximation when we are dealing with atmosphere?
Hydrostatic balance is, so whenever we make an approximation, we make it for a purpose. Okay. So by and large, hydrostatic balance is a great approximation in atmosphere. But whenever there is convection or vertical mixing, you have departures from hydrostatic balance. We talked a bit about it yesterday.
Yeah. Okay. Thanks.
Yeah.
So you presented this model with 2 modes, paratropic and paracooling. Is that similar to the Frears et al. Model? Are you familiar with this model, which has 2 modes and they're coupled and has moisture in it?
Which one actually?
It's 2008. Frierson et al.
No, I'm not aware. Not aware. But Bin Wong has written a full set of 20-30 papers on this. Frierson's GCM work I know, where he did essentially the same thing, but in a GCM. There is a model that Andrew Maida and Gual M. Khuider have written, two modes, again, barotropic, baroclimate, where essentially similar set there, their hypothesis is the interaction terms are important. So basically all the energy is coming from smaller scales feeding onto the large scale. And yeah, again, they have written a set of, I think, 10 papers or so.
Just more of a meteorological question. I was just curious how we decide a particular day for coming of a monsoon. What's different the day before or later to that?
You mean before monsoon onset, what's the big difference before and after?
No, like how do we come to a particular date for the onset of monsoon?
So this is a question which meteorologists think quite a lot about. And they have a particular threshold and some signatures for what should be satisfied so that you can call it monsoon onset. Some of the variables are related to how strong is the flow which is bringing water vapor from ocean to land. How deep is it? Is it raining enough and consistent? Does it show a particular vorticity structure? I think this is these 4 parameters usually. You can go on the website of IMD from where I stole this, and they will give you a description of what they actually do. But these are typically 4 parameters to look at.
Thank you for the wonderful talk. So my question is that when you were describing vorticity convection coupling, can we look at it in another way, that there is interaction between vorticity in different planes, different components of vorticity, one in latitude, longitude plane, and then other one in altitude and latitude?
So you are talking of not this vorticity, but what? Yeah. Some people have looked at this component, but usually this component is important while the clouds develop, how the clouds will be sheared off and so on. There is a nice paper by Rotuno and Klemp on this. You can look at this paper. I could be wrong in spelling, but by and large, Google should help you. 1983, I think. But so far as we are concerned here, we want to explain how convection moves northward or eastward, or so that means the relevant vorticity is if you like the vertical axis, vertical component. Yeah.
Yes.
Oh, sorry. I think he was before, but since you have the mic.
Okay. So my question is, like you said, vorticity coupled to vertical shear and moisture gradient. That is what determines the northwest motion and also the tilting of the vorticity with altitude. So can I say that if there is no moisture gradient, then
there is no moisture gradient,
or there is basically no moisture, if it's dry atmosphere, then such a vortex cannot be sustained or it will not have any tilting?
Yeah. So in that particular model, you can say that this is a dry model. Oops, there's too many slides. Yeah, this model, right? Oops. Yeah. This model or the one in the end?
The one in the end.
The one in the end. So can you say that?
Yeah, this model.
There's no background moisture and it's just dry problem. That's what people have been trying to do and not been able to explain why vortex sustains, right? So what they do is initialize, they put some vortex in the mix and they look at what sustains it. If there was no vorticity gradient, no convection, if you put vortex because of dissipative processes, at some point you lose energy, right? Through nice cascade of inertial subrange and so on. People have talked about it yesterday. You need some energy, continuous supply of energy for the vortex to sustain and generate more convection. Yeah.
Okay, thank you.
Vishal, I have a question on that Wheeler Killardis that you have shown. Wheeler Killardis, that dispersion diagram.
Sorry, I don't hear you. Huh?
You have shown the dispersion diagram. The Wheeler
Dispersion,
Killardis.
yeah, Wheeler-Killardis diagram.
Yeah,
Yeah. I'll bring that slide up.
yeah. So there you have shown on the left-hand side, there was the MGO, right?
Yes.
And it's probably wave number 1.
People call it wave number 1 to 5. There's a catch there that, so this is wave number 1 to 5 is where you usually have.
And what is the time period for this MGO?
So this is more than 30 days, 30 to 60, 70, 90 days.
The meridional scale?
Meridional scale for, so depends what variable you look at. If you look at wind pattern, the length scale is bigger. If you look at convection, it's much smaller, confined to equator.
So as per ocean, since as per my previous knowledge, like it is a ocean atmosphere coupled phenomena, right? This MGO. So can this ISO affect the oceanic flow to what extent?
Yeah, so people have looked at this. Usually 2 main mechanisms. There could be more, I'm aware of 2. One is because there is convection on the equator, it generates a mixed Kelvin-Rossby wave response. And associated with that, there is a wind burst. Once you have surface winds preferentially bigger at a particular location than the other, then it will have its kind of impact, its imprint on ocean through mixing, through evaporation, and so on. The other thing that people have talked about is the Madden-Julian oscillation and the cloud systems associated with it. They have a tilt, and that means if the convection system is moving, say, eastward, it preconditions things here. Convection system moves there, but it is tilted. And as it tilts, the offshoot is produced at the back, and the offshoot is quite big. If this offshoot is big, then it will interact with radiation and have its imprint again on surface temperature. And through that, it can have some ASC interaction.
So that spatial extent is what? Like meters, like for the ocean?
For the ocean, in the sense, what is the imprint of radiative effect or wind effect? Few hundred kilometers usually. Yeah. Yeah, something of the order of 20 degrees.
We have time for one, but if we don't, Vishal, can we check if there are any questions on the chat?
Online? Yeah.
Okay, let's thank our speaker, take a break, and reconvene at 11:45. Well before 11:45.